Let's put this now, let's put real quantities on here and think about what this graph is. Instead of just using the R and whatever, here's sigma 1, here's sigma 2, sigma 3, whatever you want to call it. Sorry. Ignore that. Sigma and tau. Okay? This is a plot. You could think of this as so-called stress space. Stress space means this plot is a characterization of the variations of sigma and tau. This is stress space, let me draw real space. Where here's sigma 1, and load to that experiment, and here's sigma 2 or sigma 3, whatever you want to call it, the confining load within that experiment. And if you go back to that little figure I had, this is a plane. It's called plane Z or something. Has an angle, theta, relative to the reference direction, sigma 1. That's the way that problem was set up. What Moore's circle does is plots, which I now don't have. Now I got to remember it myself. See if I can remember this. It should be sigma equals sigma 1 plus sigma 3 over 2 plus cosine sigma 1 minus sigma 3 over 2 cosine 2 theta, and tau equals sigma 1 minus sigma 3 over 2 sine 2 theta. So let's put some numbers in here on these sets of equations and see how this works. Let's make theta 0 first. It's the simplest one to do, right? Theta 0, cosine is 1. Not easy. That means I can do it. For theta equals 1, or theta equals 0, this is sigma 1 plus sigma 3 over 2 plus sigma 1 minus sigma 3 over 2. Those cancel. I get sigma 1. So sigma and tau, what's sine for 0? 0.
0.
So tau is 0. So I make an XY plot. I go out here. Sigma 1 is right there. Tau is 0, and on the x-axis is tau is 0. Let's take another easy number to do. It's doubled, right? So what happens if theta equals 45? Now what? 2 theta equals 90.
Mm-hmm. And cosine 90.
Actually, I want to, yeah. So that means cosine. What's cosine of 90?
Adjacent over hypotenuse.
What's, and then sine of 90 is 1. Okay, let's do that calculation. So sigma equals, that's 0, right? That's sigma 1 plus sigma 3 over 2. And tau equals that, sigma 1 minus sigma 3 over 2. So both of these have value now. Now I want to do this a different way because I did this backwards. Let's go one more increment, which is what I meant to do first. What if theta equals 90? Let's do these calculations and apply them, because this is easier this way. If theta equals 90, 2 theta equals
180.
So now cosine becomes negative 1. And sine is 0 again. So I come back to 0. So now tau is going to be 0, right? If cosine is negative 1, I now have sigma equals that quantity, sigma 1 plus sigma 3 over 2. But this is now negative 1, so it's now plus sigma 3 minus sigma 1 over 2. Now the sigma 1's canceled, and I got sigma 3 over 2 times 2. This becomes sigma 3. That one I can plot. That's, this is why I'm doing this way. There's the other quantity will be here. It will plot on this axis. Let's turn that around for a second. How does that represent, what does that represent back to real space? Here's the critical issue.
The minimum and the maximum stress.
1, this is sigma 3. Remember the angle theta. When theta is 0, that's that plane. Perpendicular to that is sigma 1. Well, it better be there because that's the way we define it, or whatever, right? When theta is 90, I'm on this plane. So I'm perpendicular to sigma 3, which is also has to plot there. Right? So those are the principal planes. So they better plot there since that's the way I set it up. That's the way it's supposed to be, right? But these two values then have no sigma. They have no tau value. Well, what's this other one that I calculated then? Well, let's take those numbers. Where do I have them? Sigma is sigma 1 plus sigma 3 over 2. Where's that? There's sigma 1 plus sigma 3 divided by 2 is where? Halfway between them. That's sigma 1 plus sigma 3 over 2. The average or whatever, right? This value then, what's sigma 1 minus sigma 3 over 2? That's a little harder to figure out. This is obvious. But that distance right there is sigma 1 minus sigma 3 over 2. Back to this set over here, that's the radius of a circle. Or if you make that plot, then here, I should have put units here, right? Maybe I should have put 100 or whatever. I'll come back to that. But I'll do it this way, the chicken shit way, right? There's that should be there. That's about there. The top of that graph then should be about there. So that's tau. Tau for theta equals 45. Now what's left? Well, I just fill in the circle. It turns out that all other values lie along the circle. Because this is a circular function, those values of sigma and tau are given by that equation, or those equations, right? Or in other words, so what does that mean qualitatively? Let's think about that for a moment. And think about real space versus stress space. And a variation, all this is a systematic variation of the quantities sigma and tau that are resolved across any arbitrary plane. So if I start, let me get rid of this for a moment. Let's consider real space and stress space. Let me get rid of, I'm going to leave that there for a moment. Let me move over, get rid of that one. Real space and stress space. And I'm going to consider some variations across that. So if we redraw this figure, sigma, tau, and there's a more circle here. I'm going to show half of it because the other one's redundant, right? Because once I get to here, I've already gone through 180, which is 360. So I only have to deal with half of it at the moment. There's a sign problem, but this value is sigma 1 and that's sigma 3. Fair enough? The way we set it up here, right? in every position, let's consider some, we started this one, right? There's sigma 1, sigma 2, sigma 3. I guess I should call it sigma 2. What did I call them? I keep going back and forth. Sigma 2 and sigma 3 are the same because of the symmetry thing. Reference 1 is one we just did, right? For this is plane 1. Throw that away.
That's funny, he did that with the other red one.
Plane 1. That one is junky as the other one. Where'd I put the good one? I put it over here. Okay. Throw that one away too. Yeah, I'm getting better. Plane 1 is the one where the normal parallel to sigma 1, right? So that's that one. That's plane 1. Is the sigma 1 plane. Now note, the critical thing is relative, it's the orientation of the normal relative to, that's the way it was set up relative to that. Let's take case 2. Sigma 1, sigma 2. Now I'm going to have a plane that's here, such that that angle is, say, 20 degrees. Let's call this plane 2. Theta is 20. I count in this position, theta, 2 theta is 40. I just take my protractor out. There's 40 degrees. That's plane 2. Sigma and tau for that plane is resolved in those values. It has high normal stress because it's close to this plane, but the shear stress is increasing, right? Fair enough? I keep rotating. I already did this one, so this one goes quickly. And theta equals 45. Theta is 90. That gets you here. So this is plane 3. It's here. I keep going. Last case, if I go a little further, I get a plane closer to sigma 1, so that theta, say theta equals 60 degrees.
120.
Now I have to go.
120.
I guess I did this one with 90, right?
Mm-hmm.
I have to go, I'm going to use another color here. I have to go 120. That's plane 4. What's the point here?
I don't know, that looks like 135 to me.
Well, yeah. Remember, I lost the sketching contest. Well, I didn't lose, actually. I beat Langford.
Oh, okay.
The point of this is that what that circle shows is the variation of the resolved shear stress and normal stress for different planes relative to that experiment. So once you know the magnitude of sigma 1 and sigma 2, you always know what the stresses were on any plane, relative to the magnitudes of the shear stress and normal stress. This is an indirect proof of something that takes a long mathematical derivation. Is that the maximum shear stress is always 45 degrees from the long axis, from the test specimen, or in the case of the principal stresses, it's a plane that's 45 degrees from sigma 1 and sigma 2. That's the top of the Moore circle. That's the greatest shear stress, right? And all other directions, shear stresses first increase, if you consider this relationship. They increase to the 45 degree position, then they decrease as you continue to consider different orientations of plane, with the minimum pressure across this plane and the maximum pressure across that one. That's all there is to stress. Right? There's a three-dimensional equivalent of this, you don't want to know it. But the point is, that gives you a qualitative feel, I hope, for the quantity we call stress that has these systematic variations that are related to it. Is my clock really right? It's 20 hours.
Yeah, really right.
Shit. Okay. Let me give you a. Let me quick show you something, and I'll leave you with this thought, and we'll pick it up either next time or I don't know if we get somebody to stand in on this or not. Most people don't like doing this. You can make a prediction here. You can make a theoretical prediction from this. If shear stress is what causes deformation, then the shear stress maximum, if you were going to make a series of rock deformation experiments, you would guess on a Moore diagram that the shear stress maxima are here. So you would predict that material should fail at some theoretical limit, which is its shear strength, right? That would make perfect sense. Well, guess what? It doesn't work. Instead, what's observed is this in these rock deformation experiments. You conduct an experiment at low confining pressure, or zero confining pressure, you might get this strength. At greater confining pressure, the strength increases, and then it increases and increases, which does not match this relationship, where this is a threshold value, right? Because the diameter of the Moore circle is the difference between the end load and the confining load. But these experiments show that instead the material increases in strength with increasing confining load. Or if you were to plot that on Moore circles, it would look like that. First experiment has a smaller Moore circle because it failed at lower stresses. The next one's larger. The next one's larger than that. And we'll pick that up next time as to why that occurred.